Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, it's my great pleasure to welcome Professor Raj Jain. He's a very, very accomplished person. I've actually known him for many, many years. When I was at DEC, he was a senior consulting engineer there, I guess. Invented a DEC bit and did a lot of other stuff. And since then, he started companies. He's a fellow of the IEEE. He's a fellow of the ACM. He is now a professor at Washington University, St. Louis. And he has a very interesting proposal which I thought we should hear about. So I'll just let him talk about it now. Raj.
Thank you, Victor. Hold on 1 minute. I forgot about this part here. I did bring about 10 copies of the paper that goes with it. And basically, those of you who are interested later on can take one paper. But basically, there's a paper on this. And all the slides are already available at the URL noted here. So those of you who are remote and want to get the handouts, actually, if you're local and you want to get the handouts as well, all the slides are up there on that website. I have just changed one word in the title, which was "and a proposal for the next generation." So I wanted to make sure that people understood that this is a proposal, not a solution. It's not something that we have worked out to the end of detail. What we have done is we find out what the problems are with the current internet and what we think are the solutions. And by the time this is all done, if it is like anything else we have done in the past, the solution would come out very, very different, because the real solutions will come out not from me, but by interacting with lots of people all over the world, IETF and so on and so forth. So this is just a starting direction. All right? And second thing is, please feel free to interrupt me anytime. I have asked for 90 minutes, and they have given me 90 minutes. And so that is basically, purpose is so that we can have good interaction. And that's the purpose of my being here in person. Otherwise, you could view probably all of this remotely as well. So even remote audience, I don't know how they interact remotely, but if there are any questions, I would be very happy if, to interact, agree, disagree, argue, whatever. So first of all, I will talk about what is Internet 3.0 and why Microsoft should worry about it. And what are we missing in the current internet? Current internet is such a good thing. I mean, it is everywhere. We use it every day, morning to evening, and we can't even think about what could be wrong with it. After this lecture, maybe you at least start thinking that there is something wrong with it. So we sat down and brainstormed what is wrong with the current internet, and it will turn out that it is all upside down. Actually, we didn't know as much as we know 40 years later. In 1967, when this all started, they didn't have the idea of the things that it will be used for. And so then we have proposed architecture for Internet 3.0, which is basically, we have given the name GINA, and I will explain that what GINA is. So what is Internet 3.0? Has anybody heard of it before? No. Well, at least you guys are very honest, because Internet 3.0 is the name that I gave it to something. It sounds like something that you should have known about, but it is something that I just started. So basically, it is the architecture for the next generation of Internet. The current Internet is Internet 2.0, and I will tell you why it is 2.0. And then actually that is also not universally agreed, but I will make a case for it. And so the one next generation would be Internet 3.0. And I gave the word 0 there, 3.0 actually, because of the famous Web 2.0. Today, you go out in the industry and everybody is working on Web 2.0. All right? And so now I have also started hearing about Web 3.0. Who knows? But so I just wanted to make sure that the VCs also understood Internet 3.0. And it's very natural, actually. Anybody on the street, you say Internet 3.0, they will understand what we are talking about, because NSF is actually planning a $300 million research program for the next generation Internet. but their name is GENI, GENI, Global Environment for Networking Innovation. If you go to the street and say, well, I'm going to work on GENI, then you have to explain what GENI is. And with Internet 3.0, they get it right away. And then NSF also has a program called FIND, Future Internet Design, which is the architecture part. So they have two parts. One is the test bed, and also NSF is doing it upside down. So they are first setting up the test bed, and then they will worry about the architecture. So, I mean, that way we don't know whether the architecture can really be tested on that test bed. Okay? So, obviously I don't have money for the test bed, so I'm starting with the architecture. So we will talk about the architecture of the Internet 3.0. Most of the networking researchers, actually not only us, you will hear a lot more about it from every other place. All the universities are going to work on this. If $300 million are there, you can imagine, just divide that by 100 and how many people will be working on it. I mean, everybody is going to work on it almost. And so, and not only here, I hear every other country is working on it now, because we lead the research agenda for the rest of the world as well. When people in Hong Kong or Europe or Taiwan, they hear that NSF is working on next generation, they start working on next generation. So this is the hot topic. So the question is, how would you design the internet today? How would you design the internet today? And the constraint is clean slate design. So don't worry about how it is today. But given that you know how the networking can be done, how the packet switching can be done, how security can be done, if you were to start all fresh, clean slate, how do you do it? Because if we start how to take the current internet to the next generation internet, maybe our solution space will be so limited that we will not be able to see some space that we want to see first. So we want to just not worry about the current internet, come up with what the solutions would be, and then we decide how to get there from here. Because obviously if there is no way to get there from here, we are not going to get there. So the transition is important, but for the time being, we are going to forget that. All right? So in this talk, don't worry about IP, TCP, or any of that. We are not assuming any of that. In fact, I'm going to change the whole fundamental structure of addressing and naming and everything else. Okay? So we are talking about a clean slate internet design given the 40 years of knowledge of networking that we have. All right, by the way, there was an URL in the previous slide. This is where you can find all about GENI. Yeah.
Actually, the link is dead. There's nothing.
It's dead.
Yeah.
Okay,
Yeah,
so
it's geni.net.
I would just announce that this link is dead, and people can look up for GENI plus site whatever nsf.gov, and you will find it. But this link is not good. But I don't know. I can fix it right now, right online. So I will just leave it there. So BEP 2.0, I don't need to give introduction. Basically, I think I'm going to skip this slide. There is a lot of money being invested in BEP 2.0. And all the things that you hear about today, all the famous websites that are making money and all that, YouTube and so on and so forth, they're all BEP 2.0 stuff where, the people are getting more involved. So this was just simply for the naming part. And so Internet 3.0. If BEP 2.0 can be $1 billion opportunity, Internet 3.0 is multi-trillion dollar opportunity. So it's really a lot of things, and all the big companies have to be on the top of this thing. And I will motivate that a little bit more before I go into the technical part of it. And many of you who worry about such things as the technologies and the future of the technologies and the future of the world and so on and so forth at a much higher level probably know this thing. And that is that all the technologies have this N-shaped curve. And the first part of the technology is research, when it takes a lot of time to do very little, to produce very little solutions and so very little dollars. And then once the fundamental problems have been solved, then it enters the hype stage. In that hype stage, basically everybody joins in, everybody says this is the technology which is solves all the problems of the world. And so there is very little time you can actually do a lot of problems, and there is a lot of money you can make. And then it reaches the peak of disillusionment. At that point, people find out the truth, and no technology produces what it was advertised for. And so then there is a disillusionment, and the bubble bursts. And then finally, one of the two things happens. Either the technology goes away forever, or it succeeds, but actually this curve is probably much higher. It succeeds at a much slower rate. And so what we have to do as a researcher, obviously business people have to worry about it more, but as a researcher, we have to really try to make sure that we are not working on this part or this part. If you are working on this part of the technology, you're just wasting your time because you're not going to find any funding. Nobody's going to care for it anyway. So you really want to work either in the research phase, all right, or at least in the hype phase. Now, while the word hype is bad, but that is where you really get research funding. That is where you really make the fundamental contributions, and so on and so forth. So it's really, the name is bad, but you hope that this curve will finally follow the upper curve there, okay? And so, and the business people plot these graphs for every kind of technology. And for networking, the last graph I saw was 2004 from Gartner, and for them in that time, RFID, WiMAX, these are on this side of the curve. VoIP is on that side of the curve. So really, I mean, these things have stable down, and there will be stable growth on those areas. And these areas are where there is a lot of hope. Now that graph is very questionable, by the way. Don't take it. This is somebody's view, and it's not my view either. So I'm not going to argue with as to where the technologies should be. The point was that everybody has a view, and you can put your own technologies in your own graph and your own plots, and and then you can come up with. So I'm not going to argue that whether this is really true. The point is that if you take a differentiation of the previous graph, you get another graph which looks like this, and which tells you that where the companies are, where the people are. So most of the companies, as the technology basically matures, starts first, there are several new companies that come in. The number of companies keeps going up as the hype builds up. When the hype is kind of disillusionment starts, then all the companies go away, and this is the bottom, and then this very slow growth takes place. So most of the innovators, startups, and technology differentiation takes place in this part. All right, and in this part actually there is not much money to be made, but in this part it is mostly manufacturing and price differentiation that gives you money. And that's not a very healthy thing to do. In fact, particularly if you're in the United States, if you're in some other country, maybe more manufacturing-oriented countries, you pick up the technology at that point, and that becomes Taiwanese, Chinese, whatever. I mean, I don't know. I mean, basically technology. But really, for us, we have to be here. Now, I said big companies here, and that is kind of misnomer because actually big companies can be here. And most of the successful big companies, you name it, and I include Microsoft in that, generally are here, and they want to make money by technology differentiation and not by simply manufacturing cheaply. All right? So to be here, we have to really work on this thing. And there are formulas several companies have. One company has a formula where they put 10% on distant future, 20% on near future, and 70% on today's products. So in that company, at least, the employees are told that 4 days a week you work on what we are assigned for. You have a project, you got to have deadline, finish it. 20% you work on something that is related, but your manager didn't tell you that, but you're working on your own. 1 day you are left free. And 10% of your time, which is some part of that day, is you're working on something that has nothing to do with that company. Totally distant future, your imagination. And I think that's a good formula, basically, is to let people think about what is new, what is innovative. And here, being part of Microsoft Research, probably 100% of the time you're working on these two anyway. So some part of the time you should be working on things which are not assigned by your manager, and just thinking about you're leading the company in that direction, right? All right. With that, now we come to our problem, Internet 3.0. So Internet actually has had 2 generations, although they are not named like that. And so I studied it, and I found that there is a clear direction change in 1989. So I named that Internet 2.0. Internet 1 started somewhere with this kind of picture in 1969 to 89. RFC 1 is dated 1969. So that puts a date. I know RFC 1 would have taken some years to write. So, it must be much older than that. ARPA project started a few years earlier. IP, TCP, UDP were done in this time frame, and was mostly researchers. Because I was working for Digital Equipment Corporation in 1984, and we didn't worry about TCP IP. We were working on DECnet. And so TCP IP was not something that was everyday word. Industry was busy with proprietary protocols, SNA, DECnet, AppleTalk, XNS, and so on and so forth. So this was mostly a research network. All right. In 1989, NSF gave it to the industry. They said, okay, we are not going to work on this anymore. Actually, before that, basically what happened was, that is when the industry started looking into it, and once they started looking into it, when the NSF net started becoming commercial, it's then that they found out some real problems with the architecture as it was designed. First of all, security was totally missing. The researchers didn't worry about the security, and the industry couldn't use it, anything which was insecure. So the first RFC, very first RFC in security came out in RFC 1108 came out in 1989. And then they started running out of the ownership, they started running into ownership issues. So they had to have domain and inter-domain routing, OSPF and BGP. They started running into address shortages. So then they had to have NAT and whatnot. And IPv6 was almost invented around that time. All right? And congestion control, quality of service, all the issues that we work today were done in the second phase when the internet found its way into the real world. All right? And that's when actually basically we also started working on it, because even after 1989, regardless of which company you're working for, you're working on TCP/IP. So that brings us to the two generations. Now this is not agreed upon, but I got the blessings from one of the top people. I took this whole presentation actually to Windsurf, and he agreed with this breakdown point. He says, I remember how difficult it was for this RFC 11.08 to come out, because there was such a big discussion and this and that. Security, as usual, is very contentious issue. So 1989 is the point, and just 20 years later than that, 2009 is the right time for us to do Internet 3.0. All right? And NSF is planning more like 2010, 11. But I think being part of the research, being part of the universities, we really have to start now and start thinking about it. And if you're not thinking about it, obviously, you are on the right side of the curve than the left side of the curve. And so we have to be on the left side of the curve. All right. Any questions so far before we go into the current internet problem? The interaction has been very low so far. Any question about anything I said? Yeah.
Sir, quick question. Why do you think the time is right now?
Time is right now because basically every 20 years a new generation comes up, and this is the time for the 20 years of the previous generation. There are two reasons actually. First of all, NSF thought about it, and they're going to give us $300 million, so its time is right now for us. But second reason is basically the technology turn point. I mean, it doesn't just happen, there has to be some push from somewhere, which NSF is providing that push. But also the technology has become mature enough that we need to look at, there are some fundamental problems that we'll talk about later on, that really need to fresh look at these issues, at the design principles of the previous generation. Was the same question you had?
Well, I was just going to point out that one example doesn't make a trend, so saying that one example of 20 years doesn't mean that this is the right time.
I have another take on this.
But the other thing I was going to say is there's a lot of people who would say if it isn't broke, don't fix it. And obviously, the original internet did a lot of things right, otherwise it wouldn't have gone anywhere. So and finally, there's also, I think, the problem with any clean slate design is you do have to worry at some point about deployability. And if you completely ignore the current system, in order to avoid its problems, you both won't get the good things out of it, and you won't have any clear path to deploy your new solutions. So I think it's
And your name, sir?
Brian Zill.
Brian
Zill.
Zill, okay. So the thing is, just for the recording purpose, because those are very good points. Actually, I 100% agree with you. If it is not broken, don't fix it. And then second thing is that we have to worry about the transition. And everything that I will present, I have that in my mind. Even though it is clean slate design, I have to worry about the transition, and I could give you enough examples of the technologies in the past that didn't succeed because they didn't worry about the transition. There are other reasons that they didn't succeed, but transition is important. I agree with that. But the question is whether it's broken or not, that we have to question that. And I will talk about that in the next of the slide part. You have some comments?
No, I was just
sorry, I will come back to you now. Yeah. Go ahead, go ahead.
I was just going to give a different take on why this is happening. And this is somebody else actually pointed it out. I think it's if you look at it from a pure technology perspective, you think about the people who invented or did this thing, right? They've gotten old. Their students are now at a certain age who've been working at it and sort of thinking, hey, what is our legacy going to be? So that we got to create something this new thing, right? And so in some sense, it really is driven like that, believe it or not, where all these individuals, who are now of the age where they're beyond their just meeting day-to-day things, are starting to wonder, what are we leaving behind? So they want to rethink this thing. So it's a different take at it.
Yeah, right. Yeah. So how the frontier came about, that could be, there are many reasons. Yeah. Okay.
I've heard two things motivating it. One is that the current internet is somehow deployment challenged. That many good ideas have come up, and for whatever reason, the research community has no influence on Cisco and others that might implement them. The other thing that I think that's a little dubious. The other thing is that people talk about security a lot, and so the question is, what can the network do for security, and what can the end systems do for security? So if security is the problem, where does it lie?
And you need to think clean state on that one at least.
Well, there's mobility to it.
Was there a hand here up on the side? No, that was very good. Now, you brought up an issue which I was going to bring up later, is that NSF alone cannot do it. And I keep telling the NSF managers, what they are going to do is they just have, and actually NSF is doing several things wrong in this. First, test bed before the architecture. Second thing they are doing it is top down. So they have recruited 4 professors to write the whole thing down, and which really limits it to those professors' projects and next generation of those projects. And so it's really should be bottom up. Usually, as it is done, most of the innovations come bottom up. Very few CEOs can tell somebody down that, okay, please do this, and think about this problem, and somebody starts thinking about the problem. And so basically, it just somebody thinks of the solution and a problem, and then the CEOs find out. So bottom up is a much better approach. And third thing the NSF is doing wrong is really second generation or third generation of nothing is done by the universities. Really, the industry has to do it. Industry has much more invested in it, and they are the one who can really lead it. And that's why I am making rounds of all these companies, is I really want industry to be involved in this project right up front. And that's why I'm here at Microsoft, is that I think if Microsoft got involved, Internet 3.0 has much better chance of happening than if they didn't get involved. If they didn't get involved, it has 0% chance of happening, okay, for sure. So basically, yes, I agree with that, because this is not Internet 1.0. 1.0 could have been done by the universities. Any fundamental thing can be started by the universities, but this is not fundamental anymore. This is like an airline industry. I mean, if you want to make a new aircraft, you can't start in a lab someplace. You got to go to Boeing. I mean, they have $1 billion invested there. I mean, they're not going to just change to some new supersonic, whatever it is, right? So that's the thing. Okay, so that's why I'm starting from here. And I hope that after this talk, a lot of you guys start thinking about it, and and maybe we will make it happen. Okay, so with that. So what is wrong with the current internet? Actually, it turns out once you start thinking about it, you will find a lot more wrong than what I have on the list here. I had made a list of 25 things, and I put 10 here, just because I didn't want to give a whole day lecture here. So basically, for an hour and a half, 10 things are wrong. First of all, current internet assumes that everything is live and awake 24 hours a day. Nobody sleeps, ever. If you want to go talk from here to Germany, not only you and the Germany have to be up, everything along the way, all the routers along the way have to be up. If one of the routers is sleeping or dead or broken or whatever it is, your message doesn't leave your place, and that is considered normal. Well, that should not be normal. Particularly, we should be allowing people to have communication. They should not know, I mean, regardless of what is under construction, what is along the way, or what is broken, or so on and so forth. And biggest thing is, when I have this computer and I shut it down, everything goes to sleep. All the programs, when I open it at my home, all the programs come back up, except all the network connections are gone. Network has no sleep state.
That isn't entirely true.
Yeah, that's not true.
Okay, go ahead. Yeah, your turn.
You can have a TCP connection that's open, and as long as you have the same address and when you come back up, you can reestablish where you left off.
Good point. As long as it is the same address. Can you get the same address at home?
If you have mobile IP, you can.
No. It turns out it's very difficult. And so if I am on the road, if I am in this one, well, everything else comes up. So that as long as part is the problem. So yes, it is correct. So this is limiting then, right? It is limiting that you have to have the same address. And sometimes you may get the same address, sometimes you're not, due to you. Yeah.
That's just because you're assuming you come up with an arbitrary definition of a network connection. You have decided that network connection means TCP connection. That doesn't have to be so. I mean, if you have a BitTorrent connection, or if you're doing one of these, Microsoft bits, yes, sure, your address will change.
Yeah, right. So basically, network doesn't take the responsibility; it's the application which takes the responsibility. Fine, that's right. So there are lots of applications which cannot take advantage of that. Okay, go ahead, you. Vipul, you had...
Yeah, I was going to point out, I think it's related to what Brian and Jeet are getting at, like defining what communication means. Like SMTP, for instance, emails can go out when systems on the two ends are sleeping.
Yeah, applications. He mentioned the same thing. Applications can happen, but many of the things cannot happen. And basically, and here I'm not limiting to any particular application. I just mean the communication, the fundamental process of sending packets from here to there. Now, let me give you an example where it does happen. By the way, you didn't give example that one. In all wireless networks, even when my cell phone, which is missing right now, but basically when it is communicating, it is sleeping 90% of the time. 99% of the time it is sleeping, it is awake only 1% of the time, but doesn't miss a single packet. Because the network takes the responsibility for all applications. All right? And that's how that cell phone is green, in the sense that it can run for 1 week on one battery charge. And that's what we want to see everywhere. Why just on the things which run on the battery? Everything that runs on anywhere else is already used only 1% of the time. So why does it have to run 99% of the time? So we want a green internet. Now again, you can say, well, I am living with whatever it is. Yeah, fine, you're happy with whatever it is, but we are, if you think about like an innovator, then you think, yeah, all right, maybe it is worth fixing it. All right, so that's the point, is that, yeah, go ahead.
The internet is sort of green. I mean, if I have my web session, I go somewhere to the other hotel, I open my laptop, CNN is there.
Yeah.
What do I care what my IP address is?
Yeah, but okay, all right, hold on. So what it was that the CNN was up all the time when you were gone. They had kilowatts burning there. Generally for CNN is a bad example, because there are millions of people who are already accessing. But my website is another example, which is maybe 10 people are accessing in 10 hours in a day, right? It is up 24 hours a day for that reason. And there are routers along the way which are just to have one packet going through, like router in my home, and it's up all the time. And so on and so forth. So again, the point is that we are going to design in next. Hold on, now this is enough. Now, if you want to bring up another application, I am not going to take the same example. If you have some other one, then I will take. Yeah, okay.
I have. I would argue that cell phone is even worse then, because all those towers are burning up power even when nobody is using it, right? That's why Sprint offers you free nighttime minutes.
Yeah. Okay. So basically, the choice is that so you came up with an example where one place was burning power, whereas million places were sleeping. All right. Now, then the question is whether it is more power that way, or million people burning would be more power. I haven't done analysis, but I would go with whatever is happening. So basically, here's the thing: the latest networking technologies are all green, by the way, and latest is all wireless, by the way. So you cannot design a wireless technology today, whether it is WiMAX or any other thing. WiMAX is actually the latest wireless technology too. And you go there and see how much time they spend saving every milliwatt, millijoules, whether it is Bluetooth, same thing, or UWB. I think we should just take all that knowledge and put it into the wired network as well. So here's another thing. This clean slate design doesn't mean that you have to invent something new. They are saying that how would you design the network if you were to design today? So we already have this 40 years of knowledge. We already know how to design a green network. Why not just put it in the fundamental principle of the architecture? Second thing is identity and location is one. Well-known problem. IP address is your identity and IP address is your location, and that makes the mobility complex. And we will talk a lot more about that as to what is identity, what is location, and how the IP address makes it very difficult. Yes, mobile IP is there, but it makes it very difficult. And second thing is, so IP actually is IP address is location sensitive. The example was given here that I have an address at office, I have a different address at home, I have a different address in my hotel, and other places. And of course, with mobile IP, I can probably somehow fake that address. But every time I change my location, my IP address changes. And therefore, we need ways to fake that address, or that makes it very difficult to move around. Yeah.
As a consumer, do I really care?
Yeah, no, you don't care. But that's why mobile IP is not happening. As a producer, it is so difficult, so complex that people are not really implementing it. Because the thing is, just think about it. The thing is, why is the hotel that I'm staying at is deploying mobile IP? I don't know. Basically, mobile IP has been around since '94, right? And IPv, so I can go on giving examples. So the thing is, if something is not straightforward and not fundamental part of, if it was made fundamental part of the architecture, it would be as common as IP is. Okay. Third thing is location independent addressing. So IP address is location dependent, but at the same time, it doesn't give me the location. If I give you an IP address and ask you where this address is located, there is no way in hell you can tell me where it is located unless you go through some very sophisticated method, which some big companies have figured it out, but most companies have not. So you cannot tell me whether it is in China, USA, Japan, Taiwan, let alone whether you can tell me they're in this room. All right, so it doesn't tell me anything. And if I'm looking for any services, I am looking for services next to me. So if I'm looking for MSN, I'm not looking for MSN.cn. I'm looking for MSN.us, whatever that is, right? So the thing is, big companies have to solve this problem by asking you. You go to big companies like Toshiba or some other company, they say, which country are you calling from, sir? USA, Japan? You have to tell them where you are. They cannot figure it out from your address. All right? And so it is location dependent, but doesn't give you the location. Then, and most of the services require location. It would be very nice if the network itself told me that, here is the next thing next to you, printer next to you, or whatever it is you're looking for. Single computer communication. So when it was designed, you saw the original picture of the internet 1.0, one computer here, and the challenge was how to get one bit from here to there. That was a very challenging problem for those days. Today we understand all that. In 2001, and in fact we don't even do that one computer communication. What we are doing today is really one computer is on one side, maybe that computer is very little, my PDA. On the other side is big MSN, which is millions of computers in some place, I don't know. Maybe distributed all over the world. All right. So is that the right way to communicate with them? I don't think so, because now this MSN has to figure out how to make look like one computer, and then one IP address comes in, and then fake it into some other kind of IP address, and then we distribute it, and we have all this web distribution stuff, which has to figure it out as to what this means. All right. So the distributed computers are not really correctly represented as a computer, as one computer on the current internet. They are represented as one computer, but it is the user's responsibility or the owner's responsibility to figure out how to distribute that address and how to distribute the task of that address, how to do that, right? So they didn't even think about that problem. All right. Any argument to that one? So solutions exist, by the way. Let me just say that solutions exist. So for example, when I do connect MSN, MSN somehow figures out that the previous request from this guy was sent to this server, and it goes to the same server. I hope they don't change the server every request, otherwise it will be too much work. So they somehow keep the context, right? Fifth problem, no representation for the real end system. So current internet is limited to electronic devices. I can have my PDA on the internet. I can have my desktop, my laptop on the internet. But when you want to reach me, you're not trying to reach my laptop, desktop. You're trying to reach me. So if you wanted to send a message to Raj Jain, you really have to send to 3 places, or send to one of those 3 places which I may not access. All right? So the real end system is me, and I don't have an IP address. Okay? And sixth thing is designed for research. So it was designed for research, as you saw, Internet 1.0, and therefore the basic fundamental decision was that everybody is trusted unless proven otherwise. In 1989, when the real world came in, they said no, the real principle is everybody is untrusted unless proven otherwise. Otherwise, right? So we have to start with that fundamental now. If you want to do a clean slate design, it has to start with the fundamental assumption that everybody is untrusted. I cannot trust you. I don't know who you are until you prove yourself who you are, right? So that really has to change the fundamental design. Seventh is control, management, and data path are intermixed. So in those days, 67, we didn't know what is a control. We didn't know what is a management. And now we know, right? But they're mixed. So what happens is on a wire, on a wireless link or on a wired link, if I hear all the messages, I can see the messages going between the users. But I can also see the routing messages going through. The routing messages which are going from one router to the next router, those are control messages, right? And those are going on the same wire, in the same format, same way as every other message. And therefore, anybody can say that I'm a router and this shortest path to the world is through me and everything will go to them. And this happened at an IEEE meeting just last year. Okay? One computer declared itself as the router with zero cost to everywhere in the world, and the whole network of IEEE meeting came down. IEEE which designed these networks. Right? So you can see that can happen anywhere. The reason is because the control messages are totally mixed with the data plane, whereas in the phone world, the messages which go between the switches, the routing messages, they go on a control network, which is totally separate, physically separate from the network on which your voice and my voice goes through. So by speaking, you cannot change the routing at least. Yeah, go ahead. Yeah.
That's a retrofit too, though, right?
Okay. All right. So that's a retrofit. Fine. But basically, that's why they are. Did you have another point, Ritul?
Yeah.
Go ahead.
Earlier you were talking about learning from 40 years of research, and it seems like this is one issue where you can take either stand, because there are other research showing that once you separate control and data path, bad things happen, because the control path is up and the data path is down. You're never going to figure it out. And just decoupling them actually creates more problems than it solves.
Right.
But it never hurts security to separate.
Sure, security, I agree, yes.
Okay. No, I will tell you. So there are two extremes here. On one extreme, there is no separation. On the other extreme, there is a physical separation. And what I am proposing is that we do a logical separation. In the sense that I don't mind using the same wire, but it should be such a separation that my packets cannot be confused ever for a routing message and vice versa. Basically, it's just like two T1 links. Okay? They both go on the same wire, but the packets cannot get mixed up. So it's very simple, right? So the thing is, so it's that kind of technology exists, answers exist, but we have, so basically I'm not asking that you put the number of wires by 2, multiply the number of wires by 2. I'm just saying that you keep a logical separation so that nobody can start a control plane message unless they are in the control plane. And there are ways of doing that. We understand that now after 40 years of work. So and that will solve half of the security problems. So I'm not talking about, most of the security issues actually I'm going to solve are by this method. It's just changing things around and not by encryption. I don't know much about encryption and things like that. So coding encryption, people have done a good job, and I'm happy with that. But there are several issues that we have not done as a user of those things that really making it insecure. Eighth problem. Oh, by the way, you said that it has been retrofit. I just said, okay, retrofit means originally it was different and then it was fit later on, or what was the point?
Well, I thought the famous Captain Crunch whistle was used to send because they did send signaling information over the same connections as the data, so there was ways to send high-pitched tones to...
Right. They used to have blue boxes.
Right.
Yeah, okay. Yeah, so that was all fixed. So basically, so we are agreeing that control plane has to be separated, even though in the phone network they were not smart enough to do it on day one, which I can imagine basically. They were, 100 years ago, they were probably even worse. So anyway, so that's good. The eighth problem then is, it does not really represent the organizational, administrative hierarchies and relationships. Now, this is a tough one to explain. And I have more about this to say later on, but basically, internet people in day one, really, they didn't think about the organization. They didn't think about the relationship. They didn't think about the people. They just wanted to have two computers talk to each other, somehow get the bits from here to there. But in the real world, the relationships are much more complex. So you two are in the same company. You say, well, actually, that's a bad example. You two are in the same company, but you are in different departments, and therefore you share some secrets and some secrets you don't share. All right? So there's a relationship here where there's some level of trust, and then there is a different level of trust. We got to separate you out, and right now in IP there is no way to do that. I mean, either I put a private network, and which is not a complete solution, or I just put in a public network, which is even mess. So the idea is, how do we somehow make sure that you are both part of Microsoft, but in different departments. All right, you cannot represent that. You are in the same country, so you should be trusted more than a person in China. But I can't do that. I mean, basically, so it's kind of difficult. Probably I can do China easily, but basically, I'm just saying that the organizational hierarchies and relationships are not represented very well with the current internet, and private network is not a solution. Yeah.
You can do this, though. I mean, I would think that the real issue here is that people don't want to do this via addressing.
Yeah, right. I think
I don't see where this is a problem, I guess.
No. It's more than addressing issue, because in NAT, firewall, and private networks, they give you actually there are 4 common, and I will come back to that. Please hold on to this. At the end of the talk, if you still feel that current internet is sufficient, then we can come back to it. Symmetric protocols. So when they were doing the 2 computers, they were both identical power, and so all the protocols by design are symmetrical. Everything that side A does, side B does, generally speaking. And but today we have very asymmetric situation. Most of the millions of computers are really are these PDAs, and the other end is very powerful. And so the architecture limits us for PDA to do exactly the same thing, and both sides have a problem, because the other side has somehow trying to find the TCP offload engine and so on and so forth, and they are not very successful. And this side is we are saying we cannot even do some of this high level security stuff and so on and so forth. So they are not successful. So there are issues, and if the architecture allowed any possibility of asymmetry, that may not have been a problem. So that is one thing to keep into mind. 10th. Yeah.
I'm really going to have to argue with this one.
Okay.
I think symmetric protocols are actually one of the greatest things that they got right.
As long as the communication people and systems are symmetric. As long as the communication and systems are symmetric.
I think of, say, for example, USB, which did it wrong. They're not symmetric. So we have this whole problem now with PDAs. When you connect your PDA to your computer, it is essentially a device to the computer. It doesn't have a symmetric relationship to the computer. So you can't then take that same jack and plug in a keyboard and use a regular USB keyboard on your PDA, because it expects the thing to be a device. And not a computer.
So let me just put it this way, that if the architecture limits you to one way, then the implementers cannot do the other way. And maybe in case of USB, the architecture made it asymmetric such that you cannot do symmetric tasks, which I am surprised, because I think in asymmetric you could probably very easily do symmetric, because symmetric is a subset of asymmetric. But maybe there are some implementation where symmetric is not possible because it is so asymmetric. I don't know. I don't know USB, by the way, so I'm going to take your word for it. But if the architecture allowed asymmetric, nobody can stop you from doing symmetric.
I think it's the other way around. If you have symmetric, you can do asymmetric.
Okay, all right, then we are okay. Okay, if you can do asymmetric, that's fine. And G2, you had something?
There was this big thing about wireless access protocol, right? The Ericsson tried to do. They were doubting that in cell phones, TCP and all, they just don't work. So they have to have their own protocol, right? And they basically broke up TCP connections in the middle. There's a big industry now. It all flopped. It didn't really work. Right. But it flopped not because of the symmetric nature, the symmetric asymmetric argument. It was just that they busted an architecture which didn't have the ability to handle this sort of asymmetric. The virtues of having a very lightweight protocol at the last link was quite well understood. But the fact that it didn't fit very well with the end-to-end thing got it completely screwed.
Right. Well, this is essentially an argument against the end-to-end principle, right?
Well, I know. I think let's see what he says. But I think.
I would argue that 1394 is a much better protocol than USB for precisely this reason.
You can have end-to-end.
That is symmetric, then not.
That's the point. I think you can still have end-to-end with an asymmetric protocol design. I hope that's where you're going.
I'm not basically going to argue on this point right now, because there are several issues involved in that particular issue. But I just want to make sure that the next generation is more general than the current generation. That's all I'm saying here, is that current generation has restricted itself to certain things Anybody else had a point here, or did I miss anybody? But how come the remote people are not asking any questions? Do they have ability to ask questions?
No.
Okay, all right.
I used to, not now.
Okay, all right. Yeah.
It strikes me that some of these problems are problems for the enterprise, and some of them are problems for the big internet.
Right.
So, like, the thing that made, I think, the internet succeed is it dropped the QoS stuff, which is fantastic for the big internet, but maybe not so great for the enterprise. And same with security.
Many things. Yeah.
So do you?
Yes, so I'm going to talk about that. So that you brought it up. So basically, I am designing the architecture here, and if I say in the architecture you can do so much, the next thing is the implementer, the Cisco. They are going to say we are going to implement only so much, and Microsoft on the software side, and Cisco on the hardware router side, and all that. And so the rest of the world cannot use anything which is not implemented by these guys. And then those routers are going to be bought by carriers, ISPs, and they are going to limit. They're not going to have all the features enabled. So even if a router implements mobile IP, a carrier may not enable it. Okay? So that is what the implementer is. Now the user gets only so much, because if carrier is not implementing it, user is not going to get it. Now, then when it comes to my home, I don't even touch it anything. So I probably limit it to even default set, which is smaller set. But if the architecture starts here, then the user gets very little. So I'm going to start actually very flexible. And sometimes I'm overly flexible, and people are going to say, wait a minute, this is impossible. Well, this is not possible, but I am going to design for the next 20 years. And so, yes, basically, this is the architecture I'm talking about, and I want the architecture to allow this possibility, and you can limit it to whatever you want. Okay? So stateless. Now, current architecture has a big principle of design, that is stateless design. When we transfer a packet, we don't remember it. And when the next packet comes in, we handle it, as if nothing else happened before in the life. And so that is called stateless. We don't keep state of the packets. And that is good. However, that is why you cannot get the QoS, because QoS is all about remembering the previous packets and somehow, giving guarantees between the inter-packet times for the packet throughput, for the flow throughput and all that. The whole QoS is about state, keeping the state. And so those two things are causing so much problem that, basically, all the intermediate things are being discovered, but either rejected by the user or rejected by the implementer, one of the two. Okay, so the implementers keep coming up with stateless protocols, and the users keep saying, wait a minute, I really need this. Now, so there is a fundamental conflict, which is basically has to do with having no state. Now, again, so these are the 10 problems. Now, I have more, but I'm not going to talk about them, and some of them there might be some more in this paper. There are 10 copies of them here, and you can also download it from my website. It's right on the front page. Some more problems, but let's just talk about the solutions. So first thing is, the solution that we have is called GINA, Generalized Internetworking Architecture, and the day when I was naming this thing, I was just playing on the word GENI, but so GINA was my answer to GENI, but I think Internet 3.0 is as good enough, whatever it is, but this is architecture. What I did was I studied how the things are done in wireless networks that are different, how they are done in optical networks, how they are done in planes, airplane networks, automobile networks, on wired phone networks, cellular networks. Can we take the best of them and put into the next generation? So this is how we design this new architecture that I'm going to talk about, new proposal. Now, this is a proposal, so I have not solved the problem to the nth end, and that will take 2 years. But at least, I'm going to give some directions, and we are not going to agree on many of the directions because I don't have the answers, right? But so this is what I've done, is develop a consistent general purpose evaluable architecture that can be customized by, like we talked about, implementers, service providers, and the users. And I've taken it from all possible sources that we know about networking. So first thing it does is, and this is well known in the IP community also, that we need to separate ID and addresses. I did, as a user, need to know nothing about the address. We just need to know the IDs, and that way it allows mobility. Second thing is, we distinguish between the logical and physical connectivity, and that point will take some time to discuss, so I will leave that alone right now. Hybrid. And when 1967, Kleinbach and others sat down, their challenge was how to do packet switching. We didn't know how to do packet switching in those days. We knew circuit switching. So their circuit switching was the enemy, and they discovered a technology which didn't use circuit switching. We just used opposite of it, packet switching. Today we know how to do both. In fact, there is no reason that I should not allow to have circuit switching on the same wire on which packet switching is going on. And most of the wireless networks today do that. So if you have Bluetooth, your audio communication is circuit switched, and your communication with GPS is packet switched at the same time. Okay? When you have WiMAX, you have T1 links going on a circuit switch, and and then you have an ATM and so on. I could go on and on. Okay, so all of those things allow you circuits. So we know how to do circuits and packets at the same time. So why leave it alone? Okay. Third thing is for the delegation to servers. And so basically, not everybody has to do everything else. And if we can find a trusted party, then we can delegate the task to them. And so many of the things that little devices don't have to do. And that will allow very simple devices, and that will allow much of the energy conservation. Control and data path separation. These are two separate things, and we want them to be logically separate. And that way what happens is once you have logical separation, you could do a lot more on the data path. Data path then basically, as we know, could be a power grid, could be a wavelength router, could be a SONET. It doesn't have to be even packets. It could be anything. It could be circuits. Then service-based IDs. And then the IDs don't have to be for computers alone. IDs could be for people. IDs could be for services, and so on and so forth. And then you could do distributed services more naturally, and will allow you M by N multicast, M by N cast. So names, IDs, and addresses. So my name is John Smith. My ID is my social security number, and my address is 123, 1234 Main Street, whatever. So the key thing is that the address changes as you move. You go home, your address changes. ID remains the same. You are still Victor Bahal when you go home, and you are still Victor Bahal when you come to office. So your name doesn't change, your ID doesn't change, but your address changes. And examples of names are Microsoft, DNS name, Microsoft.com. Examples of IDs are cell phone number. Your cell phone number is not an address, it's an ID. When you go from here to St. Louis, it's the same cell phone number, right? And so that is an ID, as opposed to the wired phone numbers. The phone which is on the desk is really an address, because if I take that and plug it in St. Louis, it will never have that same address. All right, unless I do some magic thing, which I can, But the thing is, generally it is in location based. 800 numbers are IDs. Ethernet addresses are IDs. Even though we call them addresses, they're not really addresses. My Ethernet address doesn't change when I take it to my home, right? So it is an ID. Skype ID is an ID. VoIP phone number is an ID. You can take it to India and have your area code 408 or whatever ring in India. So the idea is those are all IDs, even though they might be called addresses. And some things which might be called IDs might be addresses. So basically, the idea is anything which is location dependent is address, which is not location dependent ID, and the name and the IDs are same, except that names are more for human consumption, IDs are more numeric quantities for machine consumption. So object in GINA, we have objects which are the end systems, any addressable entity and an object, and it could be computer, router, firewalls, but it could also be a network, it could be a human. So that is the thing, there is no reason that I should not have a GINA address. A company, it could be a department, it could be a city, it could be a state, it could be a country, it could be a power grid, it could be a process in a computer. And anything that is addressable, a group of those things also has an address. So basically, you could decide arbitrarily that this is an object, a set of objects is also an object. So basically, it is a recursive thing. So oftentimes, I don't know who to send the letter to in Microsoft. I just send it to Microsoft. That's it, period. Whatever Redmond Way and whatever, it comes here, right? And then somehow it is distributed to the right place. On IP, so basically, so this is what will happen in GINA is that you could, any of these things will have an will have a name and ID. So you can connect to a human, you can connect to an organization, you can connect to a department. And each object also has a name, where the name is for human use, ID which for computer use, and addresses which changes all the time. They could also have other attributes, such as they could have keys, they could have power size, they could have storage capacity, other things. And so you need to have at least one or more IDs. You don't need names. If you are all computer to computer communication, you don't need name. You can have 0 or more names, or 1 or more addresses. You need at least one address to be able to be reached you, and 0 or more of other attributes. So now when you connect to an ID and not an address, and that way it allows mobility. So anytime you want to talk to me, you just call Raj Jain, whatever my ID is, and you don't have to worry about what my address is. So the names and the IDs are actually logical concepts. So object names and IDs are defined within a realm. And a realm is a logical grouping of the objects that have a certain level of trust. All right? A good example is my home, is a realm. Another example is your department. So networking department and Microsoft Research, there is some trust between the people in that group. And Microsoft is another realm, actually. So it turns out that the realm could be part of other realms as well. So a logical grouping of objects that have a certain level of trust. Objects inside the realms communicate with each other at a higher level of trust than objects outside the realm. And realm managers set policies for packet crossing the realm boundaries. So if some information cannot get out of the research department, it has to get approval from certain people to sign off before it can get out, right? So that is where the security issue comes up. So basically, you have to follow the policies. Objects can be and generally are members of multiple realms. So Victor Wahel actually is a manager of research and also a dad, is also a chair of some conference, SICOM. So these are all different realms that he's a member of, right? So the objects I have similarly have different, they could be member of any realm, and these are logical things. So I could instantly create a relationship, and I don't have to worry about it because that realm is a logical thing and not a physical connection. Realms can be treated as a single object, have name, IDs, and addresses. Realms are recursive. A group of realms can be one realm, and the boundaries could be, these are dotted boundary, by the way, you can see the dashed line. These are logical boundaries, could be organizational, technological, governmental, ISP, whatever reason you want to say that this group of people are separate. Oh, sorry, this one. So, a group of realm is a realm. Okay. Now, IDs, basically similar to what we do on SNMP, the IDs are organized as in a hierarchy, and it is not like DNS, but more like SNMP, where you could be part of multiple domains and realms. Actually, we call them realms here. So this object is part of two realms and could have multiple realms and can be reached from whatever way people find it easy to reach. So these are basically not globally unique. Neither the names nor the IDs are globally unique. They are just done to be unique inside the realm. Addresses. Now, addresses are totally different. Addresses, on the other hand, are physical, and they indicate physical point of attachment. So I have an address 131 Front Neck Forest, and I paid few $100,000 for it. If I want 132 Front Neck Forest, I need to have few $100,000 more, right? So addresses don't come for free. If I have an address, which is, actually you saw the examples of the addresses from Sprint, and I want another one from some other company, I need to pay for that too. So the addresses are really something which are different. IDs come for free, but the addresses come for money. And they have physical point of attachment. So basically, the connectivity, physical connectivity, is nothing to do with the logical relationships. We have to separate that out. So the computers might be connected this way, but this is not how they want to be connected. I mean, if they were allowed to be freely connected, they would have a different relationship. So we have to separate that out, physical and logical. So on the physical front, we call them zones, and objects in the current zone is sufficient to reach. So I mean, there is some connectivity here and physical grouping of objects, but it does not imply trust. So even though we are on both same Sprint network, but I don't trust you. I mean, I don't want you to look at my packets, right? So we both subscribe to the same cable company. Doesn't mean that, I want you to be able to see my packets, and so on and so forth. I could go on giving examples of zones. So zones are objects, and so basically, again, this is a recursive definition. And so zone hierarchy is the network structure, physical structure hierarchy, which is different than the logical structure. And I will give you examples of how the physical and logical connectivity are different. Physically and logically connected, which is all computers in my lab. They are connected together with one hub. So they are physically connected. And logically connected, they trust each other. That's my private network. And I have a firewall around it. But that's all the current internet allows me. There are other possibilities that it doesn't allow. We are physically disconnected but logically connected. My home and office computer, I have tough time getting them together. If I want to reach my office computer from here, I have to work very, very hard. Yes, it can be done. Sorry, but it is not very easy. All right? Because internet IP doesn't know that these are the same person's computer. All right? And there are many, many applications I can come up with, which I can do, and many applications I cannot do. Most often what happens is when I want to do that other application, I have to fake like the other application. HTTP can get through somehow, so everybody is going through HTTP as a transport and trying to do whatever else you want to do. But that is not how it should be. If I given a choice, I would design an architecture which will keep the logical relationships in mind and the physical relationships separate. Then physically connected but logically disconnected. That is all the passengers on the plane. I was writing this slide on the plane. Immediately example came to me, if the person next to me is probably using the same wireless Wi-Fi connection and probably can hear all my wires. Right now they can't even have wireless, but I'm just telling you someday. So the idea is that physically connected, I don't mean that we have a trust here. So are people in this room right now? I mean, you don't want me to hear your computer thing, because I'm a visitor. So visitor are a wireless network. So these are all logically and physically connectivity is different, and we need to somehow separate that out. So that's why we have these zones and realms. Now routing today is very limited in the current internet. In this GINA internet, basically we will have multi-levels of routing where the number of levels is right now infinite. You could limit it to whatever number you want in the implementation. But basically, if I want to go from here to there, from here to Germany, I don't need to know the path all the way across. All I need to know is how to get from my home to my car. I want to find the optimal path, and I have that database pretty well set, and that's all I need. Once I get into my car, I let the GPS take over, and that takes me to the airport. That database is all set for the GPS. They don't know much about the aeroplane network, but once I reach the airport company takes over, and they have a good database of all the airports, and they have figured out how to get me from there to Germany. Once I get to Germany, then again reverse takes place. So each of these code zones have their very little database and some idea of where Germany is. I mean, you don't want to end up in Russia, because you went to the wrong airport. So basically, the idea is that it is hierarchical and it is limited thing, and for everything actually there is a solution which they understand. So it makes it very, very scalable, very highly scalable, and under control of the entity that wants to control it. And by the way, this is all not new very much, because we all learned all this in ATM days. In ATM days, they had PNNI, and much of this has been worked out as to how to do hierarchical routing and all that, right? So some of that can be borrowed and brought into the internet. Server objects. So now each realm has a set of server objects. You could have a forwarding server, authentication server, encryption server, storage server, transformation server. Some objects have all the servers built in. So you buy a big Cisco router for $200,000, it has everything built in. But if you buy a $50 device, it doesn't have anything built in. And what it does is, it relies on other servers in the realm. Forwarding servers do the forwarding. Encryption server encrypt the packet. Authentication server add their signatures to the packets. And the storage server store the packet while you are sleeping. And the transformation server transform the data. And they could even bake up the objects. And basically, this allows you persistent connections. And in fact, this was added by Windsurf. He says that I want persistent connections to be across a system restart. So I don't want my TCP connection to go away when I reboot my computer. Well, not only that, he says I want to update my computer. I want to change the hardware, and I don't want the connections to go away, because I'm talking to Mars. If I have to reset a connection, I have another 6 months before I can get another connection. So he wants things to be really persistent. And that is kind of difficult to do today. So basically, now remember, this is all in a realm, and so basically this is a trust zone. So when a packet leaves my home, my authentication server authenticates that this packet came from Rajan's home. You cannot find out whether it came from my computer or from my son's computer, but at least you can be guaranteed by all the encryption techniques that this came from Rajan's home, because the authentication server put a signature of the realm there. All right? And so similarly, when it leaves the United States realm server puts a signature on that one that this is coming from the United States. So you can be guaranteed that it didn't come from China. And so on and so forth. Now, again, you could do it at the application layer this one, but this architecture will allow you to do it at basically a part of the networking services that you're getting. Okay? So server allows you simple, energy efficient end devices, and not everybody has to do everything they do today. Packet headers. The next thing I had to think about was what really goes on the headers. And the answer is it's not the address. The address does not belong to the packet header. What belongs is the ID. So basically, I want to go to some place, and I know his computers are maybe Victor Behel's ID, because I know him. His Victor Behel's ID is victorbehel.microsoft.com, whatever, right? So I put that in, and he might have gone to some place. I don't know. He may not be in Microsoft Redmond or Bellevue. He might be in China. Who knows? So all that part basically will be translated. The ID will be translated into address by the network. And so network takes the responsibility. It's very similar to what the cell phone people do. Now, I'm not proposing that you do exactly the same thing, but there are many technologies known today as to how to translate IDs into addresses. And you can use any of those technologies, and at what point you do translation is also question mark, which is basically, in some cases, the receiver says that I don't want to send it to Russia. If Victor Behel is in Russia, I don't want to reach it. So I want to put an address. So yes. So the header can have both IDs or addresses, and at some point the IDs will get translated to the address, because if you want to reach somebody, you need to know the address. So translation can be done right up front, right on day one, by the sender, or it can be done by the network, or it can be dictated by the receiver. And so the receiver could dictate that, look, I am in Russia and I don't want to receive any packets from my email here, and so even though, sensitive things, if a message is from Bill Gates, yeah, maybe, or something like that. So there are some policies that he could set up, and I'm not giving an example of email. But basically, he could set up a policy as to which packets get forwarded and which don't get forwarded. So all that can be done from this ID to address translation. And finally, packet and circuit switching. So right now, the good thing about packet switching is good for sharing. Packet switching is very good for sharing, but circuits are very good for isolation. If you don't want anybody to see your traffic, you have to get a circuit. That is why T1 circuits are still so popular, because DARPA or or Microsoft or any other company doesn't want any other company to see their own packets to be mixed in by somebody else. So they don't want to take anything which is not a real circuit. So anything which is critical. And second thing is, isolation also means guarantees. Circuits are good for guarantees. All right, and that's why we end up getting these T1 links, because we have guaranteed 1.5 megabits, and so on and so forth. I could go on and on. So the idea is, why can't we do both of them at the same time on the same wire, just like the internet wireless people do. So most of the latest wireless devices offer both circuits and packets, and we should allow both. And then we introduce the concept of multigrams. So normally datagrams, which we already understand very well, multigrams are multiple packets which are related somehow. Okay, and then flows, which are much longer term things, and then streams, which are fixed. So there is a whole level of things between a circuit and a packet of connectivity that can be done. Control and data plane separation is very well understood now with basically GMPLS and everything coming up. So I wouldn't go too much there. But basically, control plane is separate, logically separate from the data plane. It could be on the same wire, it could be in the same routers, but inside each router there is a wall which says this is a data plane, and and this is this one, and this allows very powerful techniques. Security. So the security part is basically, there are many issues. First is, we will have a multi-level architecture. So every time you enter a realm, the realm will check you out. So there are gatekeepers on the entrance, and actually security is one of the end policies. There might be other policies that if you are Russian, you cannot enter USA. I don't know. Some kind of policies could be made. All of those things would be done right at the entrance, and then authentication checked to the realm. Once you get into the country, once you get into the realm, then we don't have to be checked. This is like what is done on the airport today. Once you show your passport at the customs, after that nobody asks you on the street, even if you're Russian. So the idea is that there is certain authentication which has already been granted to you, and that can be used, and there are many other techniques we can use for security. For example, when I came into this room, everybody trusted that I am Raj Jain. Why? Because Victor Well said so. And so you didn't go and verify my social security number or anything else. So the real security is not X509 certificate, which comes from the root, but from introductions. So I put here, personal introduction is a certificate. And so there is a whole method of distributed security where you really don't have to have centralized everything, because there are certain trusted objects, and based upon their trust, you trust the other objects. and group authentication and authentication multiple levels. So if you have been allowed to get into country, doesn't mean that you get into every city, and particularly you probably cannot get into Pentagon. If you get into Pentagon, then you cannot get into every building, and so on and so forth. And so basically what happens is VPN and firewalls, which are really a patch to the IP architecture, and they have problems because of that. And as you saw, that they don't allow you many things that you really want to do, and they will be logical part of this. So gatekeepers, I already introduced the word. Gatekeepers actually belong to the realms, the logical structure. Each logical structure has many policies, including how much bandwidth you can use, or it could be, or what you're allowed to do, what you're not allowed to do, and all that can be done by these objects called gatekeepers. So the difference between gatekeepers and servers is, in my view, servers are designed for the bottom, for the people to use and ask for help. Gatekeepers are designed for the top, for the CEOs to monitor the policies. Okay, and so both of them are servers, but they are serving different interests. Okay. So the servers, like storage servers and things like that we talked about, they were helping the computers to get job done without doing it, whereas these gatekeepers are there to monitor and enforce the policies. That brings us to almost to the end of this talk. And this is one slide which talks about the difference between Internet 1 and Internet 3. You could put 2 here, and most of this will still apply. Many of these will still apply. But basically, first thing is, Internet 3, we will assume that things are off unless we turn them on. Okay? And so it starts with the fundamental assumption that the communication basically doesn't, you cannot just assume that everything is on. Mobility, it assumes that the thing has moved from where you saw it last. It's not there anymore. So you cannot assume that the same address, you can use it again. Computer-human relationships. You talk about many things. We talked about relations, physical and the logical relationships, and this is more for design for the personal communication, not for the computer communication. See, original thing was designed for computer to computer, and so they didn't even think about people because there were too many people per computer. Now this thing has changed. We have many computers per person, and then basically, it's the person that you are trying to reach and not the computer. So end systems could be anything, and then protocol symmetry, asymmetric we talked about. Research, no trust, because it is designed for commerce. Ownership, there is a whole hierarchy of ownership, administrations, and communities. Sharing and isolation both are allowed. This one has difficulty giving you isolation. It's very good for sharing, but isolation has a difficulty. And that's why we cannot support much of the critical infrastructure. For example, can you think about putting the defense infrastructure on the same as in current internet? It's very difficult. Okay, challenging problem. And switching units is packets. Here could be circuits, packets, wavelengths, whatever you want to switch. Applications, is up to your basically imagination. So that brings us to the final slide, summary, and 5 key points. First point is that Internet 3.0 is the next generation of Internet. It must be, and out of 10, if I have to select 3 things are security, mobility, and energy efficiency. All right, and we have so many other things, but those are the top 3. It must be designed for commerce. So basically, we really have now, forget about the research part, we really have to go to the companies and ask them, what difficulty you are having, where you have to spend most of your money in networking, where your billions of dollars are going. Go to MSN and ask them. All right, how can we make that fundamental part of the architecture? How can we make that easier? Right? So it has to be designed for commerce, and not just basically because I have this idea of my previous whatever it is, and I want to make next generation of that one. And that is how that is why I differ from NSF. And active industry involvement in design is essential, and that's why I'm putting together a whole set of companies with WashU as this WashU location, whole set of companies that are working with me, and I in personal meetings I can talk to you about that. Is that are helping us put together this whole program of having a parallel program run by the industry. Okay, and my purpose of visit today is actually to help Microsoft join this effort. Our proposal, generalized internet architecture GINA, addresses many of the issues that we have brought up. Now, as I said again, there is a paper which was written about a year ago So many of the thoughts that I have today will not be here, and I have about 10 copies of this. So some of you can pick it up. Others of you can download it. It's on my website, which is basically, if you forget everything else, just say rajjain.com. It will take you to my website. Or if you just remember on the first slide whatever I had. But so any final questions? Yeah.
So Raj, in your conversations with industry, where have they pointed out where the dollars are being spent? Where is the cost of networking? What are they telling you?
Okay, let me tell you one thing. I have talked to DARPA, I have talked to industry. Everybody is interested in security. All right? And NSF knows that. They said that we don't need to justify. When we go to the Congress and we say we want $100 million, you just tell them we need it for security. And they will give it to you. So everything else is secondary. All right? However, I mean, there are two ways to do security. One is just, patch it more and more and more and more, and then people will unpatch it, which is actually a real world anyway. So, and second thing is to start this clean slate here. And with that, fix other problems. So, answer to your question is security. Yeah.
Okay, I have a question. To me, I think denial of service is a big problem in today's internet, because for other security problem, somehow I can block all the traffic coming to my computer. I'm okay. But if I'm operating a network, I cannot stop people sending me packets. And I didn't, maybe I missed it, but I didn't see a discussion on that.
No, this is all part of policy. So basically what will happen is one of the policies, which is, we don't call it security, but one of the accessibility policy is between 9 to 5 to 9, for example, Victor Vahel cannot be reached on the cell phone except if it comes from person XYZ. So this is his receive policy, right? And he registers it with his server, local server, and all that, right? And with that, some of the packets will be filtered out at the local server. Now that local server could also register with the US server, and the packet will not even enter the US if they don't belong to that category, whatever it is. So basically this is a matter of enforcing the policies at different levels. So the idea is, yes, so the undesired traffic has to be dropped, right? Right now, I mean, it drops at the final endpoint. It comes to your computer does this, spam filtering and figures out, for spam it works, but for maybe other things it doesn't even work. So who comes to my website, I have no control over. And they can just block it, and they can do the denial of service attack and everything else, right? But the whole policy thing is having difficulty right now in the current internet architecture.
Yeah. And I agree with you about the zone. The realm, because we need the law enforcement as what we have in the realm.
Right now you can't even tell that this is coming from China. Every day I get messages from US bank and whatever bank telling me that everything I have done is wrong. Why? Because nobody can figure out where they're coming from.
Well, they know they came from China, but they can't do anything about it.
Yeah, they can't do anything about it, right?
Tell China Telecom they don't care.
There's a big scalability problem with a whole bunch of your plans here. Just to use the example you just showed, if you can't push out Victor's personal blocking information all the way out to the edge of the U.S. server if you want to do that for every 300 million people that live in the U.S., right?
Yeah. No, please. I'm not that smart. So don't expect the answer to come instantly like that. This will take 5 years before I have a workable answer.
Well, it's not clear to me. Well, I guess my point is it's not clear to me that this is a problem with the internet architecture as opposed to just a problem that's independent of the internet architecture.
No, I think...
because I think if we could solve these scalability problems, we could do these things with the internet today. I don't see where it's a problem with the architecture.
Suppose the current internet architecture, he just gave an example, was that suppose I want to block all packets coming from CN or CN domain, just for the heck of it. I mean, it's not that all packets are bad, but suppose I want to do that. How does MSN do it?
You could very easily do that today because with the registries, the Asia registry for all of China.
Yeah, they're not contiguous.
You could look at their...
I know, you go through a million...
It's a scalability issue.
That's a scalability issue, right there.
It's not a policy issue. It's not a problem with the internet. It's a problem with the
first of all, okay, I mean, we can go into discussion of policy issue is actually a big issue. That's why there is a whole policy group at IETF. I mean, and they have been struggling. Mobility is a big issue. That's why there is a mobility group at IETF. QoS is a big issue. So these are all big issues, and they have not been solved in 10 years, right? And I'm not saying that I will solve in one day, But what I'm saying is, if you start right from today, if you're going to start clean slate, you know the problems are there, and that so we make that architecture, and scalability will be one thing. Obviously, I am not going to do anything which is not scalable. Otherwise, I would have just beaten myself up for 5 years for nothing. Where's the hand up here?
Yes, I'd like to add a comment on his question about denial of service. If you put this gatekeeper element in the network, and if you do a denial of service attack on the gatekeepers, aren't you simply increasing the problem?
Okay, all right. Okay, again, this is a detail. So don't take. See, thing is, when I come with this, I underline the word proposal. I just underline the word proposal, right? And that requires millions of dollars to become a solution, and few years, and few hundred people. So please don't kill the solution. Don't think that is a solution. I just giving you a direction. Yeah, I mean, I know. The thing is,
I guess I don't see anything here that hasn't already been proposed or thought of as well known.
Quite possible.
Except for all the problems with these proposals are also well known.
Okay. So here the thing, that is by design. So I have not done anything which is not new. What I have done is I have taken it from many places and put them together. And so if it could have been done in cell phone network, I have taken it. If it was done in some other places, I have taken it. And some of it has been done in wireless networks, which is actually a network, right? Part of the internet also. So I have taken it. And all I'm trying to say is that we have to start clean slate design. We should put all that as bottom and not at the patches in the top. See, right now, many of these things are patches in the top. And I'm just going to make it so that everybody benefits from it, and uniformly, and it becomes more natural part of this rather than, and so you start the connectivity. I mean, I don't know how you do, logical connectivity. Yeah, you can do it, but it is so difficult, and that's why it is not getting done. You had a question, comment?
Okay, I think, well, so thank you very much.
Thank you. And, yeah, I really appreciate all the comments, and because this is the kind of discussion.